Please follow along with me in WebMO. We're going to work an example that's in your notes. We'll work the example of ethylene. Let's build it in a new job. The molecule ethylene is just 2 carbons and a carbon-carbon double bond. So make that carbon-carbon double bond, add the hydrogen atoms. Then let's do a comprehensive mechanics that gets us an approximate geometry. Now let's move on and do a geometric optimization with a MOPEC calculation. So choose geometry optimization, run that job. It'll take just a few seconds. When you refresh, the job is finished. And now we've got an optimized geometry that we're going to use for molecular orbital calculations. So new job using that geometry. Move on to the computational engine, again MOPEC. This time the job we're going to run is the molecular orbitals. Run that job, and when you refresh, it should be finished. It won't take too long. Small molecule. So in the molecular orbital viewer, allow that Java applet to load. All the atoms are numbered consecutively. Every atom has a number, and we're going to use those numbers when it comes time to interpreting the molecular orbitals. If you scroll down, the molecular orbital occupancy table shows 2 electrons in every orbital until we get to the molecular orbital 6. The 6 to 7 molecular orbital is the HOMO-LUMO gap, and you can see the big difference in energy between the HOMO-LUMO gap. So now we look at molecular orbital 6, and we can see it's a pi molecular orbital. Now let's go through each of these molecular orbitals. At the bottom, we've got a molecular orbital that we're going to find is made up of only s atomic orbitals, and they're all the same sign. Next, we have a molecular orbital that's also made up of only atomic s orbitals, but it has a nodal plane that separates the left half from the right half. And so hopefully you can see the connection between the picture in the notes and on the right-hand side and the molecular orbital viewer. Let's move to the next orbital. It consists of both s on hydrogen and then p on carbon. There's one nodal plane, and that nodal plane separates really the front half and the back half of the molecule. So hopefully you can see that plane in a top view and the molecular orbital viewer. Also part of the sigma framework is the 4th molecular orbital. That has nodes right at the carbon atoms. So notice the molecular orbital picture on the left-hand side and see those planes that exist right on, centered on the atom. Those ought to be a sign that we'll be using p orbitals on carbon. Now we have a s and p combination that results in 2 nodal planes. Hopefully you can see both of them. One of them separates the front and the back, or the top and the bottom, and then the other nodal plane separates the left and the right. Also part of the sigma framework. Now we move to the pi orbitals. These orbitals we're going to find have only p contributions. The hydrogen atoms don't make any contributions to these orbitals. The first pi molecular orbital has a nodal plane that plane is on the same plane as all of the atoms. And perpendicular to that is the z-axis, which is where the pz is located. And the final pi orbital consists of an out-of-phase combination of the pz's, and it ends up showing 2 nodal planes, one that lies in the plane and then one that lies perpendicular to that plane of the molecule. Now let's relate the pictures to the eigenvector table.